Hey, welcome back. So we are starting our next unit here, our unit about electrons in the atom, and we're going to start by taking a look at some of the different models of atoms through time. So atomic models we're looking at today. So today we know that electrons exist in what we call orbitals. These are three-dimensional shapes that surround the nucleus. And there's various shapes. So here's an s orbital, it's spherical, just surrounds the nucleus. Here's a p orbital, kind of looks like a dumbbell. Here's a d orbital, gets a little more crazy there. An f orbital, way more crazy. And this one here is also an f orbital, but even a different shape. So these are the orbitals, these three-dimensional spaces that electrons exist around the nucleus. When you put them all together, so here's an atom that has a couple of s orbitals, a couple of p orbitals, and this is what atoms with their electrons look like. And this is known as the quantum mechanical model, the QMM, the quantum mechanical model. And that's what we're going to talk about a lot this chapter. So how do we get here? How do we get to that? Well, we have to rewind a little bit, go back through about 200 years of atomic history to this guy. So John Dalton gave us the first definable viewpoint of an atom, and it looked like a marble. So you see that here? Dalton's model looked like a marble, and a lot of his theories, he was kind of the first one, it was early 1800s, and he was the first one to really write down and propose theories about individual atoms. And a lot of his atomic theory is still held true today. So it was in the late 1800s then that these next two gentlemen come into play, Thomson and Millikan. And they worked with the electron. Now, it's important to note that the discovery of the actual electron itself is not attributed to any one person. But by the late 1800s, it was pretty widely accepted that there was some kind of negatively charged particle in all matter. J.J. Thomson, what he did is use the cathode ray tube. We see that here. It's going to get that positive node here and a negative node, and he'd shoot beams of ions through this little slit here, and they'd come to the back side, and you could record where they hit on this back side. And what J.J. Thomson did is use this cathode ray tube to calculate the mass to charge ratio. So how big is the electron charge compared to the electron itself? And that's where we came up with the charge of an electron, which is now widely known as -1. Robert Millikan, not too long after Thomson did his work, Robert Millikan was able to do what's called the oil drop experiment to figure out the actual mass of the electron. So Thomson figured out the charge to mass ratio, and Millikan figured out the actual mass. And the mass was calculated at a very small amount, 9.1 times 10 to the 28th grams. I think that should be -28 grams. It's a very small amount. And essentially, in chemistry, we measure it as essentially zero. We say mass is essentially zero because it's such a small, negligible mass. When you get to physics next year, they do a lot more work with the mass of electron. It does come into play, but for chemistry, we in essence call it zero, mass of zero, very small particle. This work led Thomson to conclude that the model of an atom should be kind of like what he called plum pudding. It's a large ball of positive charge with these little negatives sprinkled in. I figured there had to be some positive charge because we know that atoms themselves are neutrally charged. So if you have these negatively charged electrons, there must be some positive charge counterbalancing them. Why plum pudding? Well, I guess it's a popular dessert in England. I wouldn't know. I've never had it myself. But here is a picture of actual plum pudding. It's like bread with plums kind of baked inside. And so those electrons were kind of like the plums. To you and me, we might think of it more like cookie dough, perhaps chocolate chip cookie dough, where the dough was a big positive ball and the chocolate chips sprinkled inside were the electrons. That model did not last long. So in 1911, Ernest Rutherford did a very famous, what we call gold foil experiment. And what he did is he got a very, very thin sheet of gold foil, so he had hoped it would only be 1 atom thick. It was a little more than 1 atom thick, but he fired alpha particles at this gold foil. And his expected result was, if it were the plum pudding model suggested by Thomson, then Rutherford said, hey, what should happen is those alpha particles should travel straight through and hit the other side. What did happen, though, is that most of the particles traveled straight through. So you see these 4, 2 on top, 2 on bottom, but some of them kind of ricocheted off. They hit something in the middle and were deflected. Some came straight back, some went off at weird angles, and this surprised Rutherford. He actually very famously said it's akin to shooting a howitzer, it's a huge gun, at a piece of tissue paper, and the shell, the bullet, coming back to hit you. So it was very surprising, Rutherford's gold foil experiment, but it led him to realize, hey, we don't have a big, gigantic ball of positive charge with negatives mixed in. Instead, we've got mostly an area with negative electrons, and then one small, tiny, little, dense core that's positively charged, and that's what we call the nucleus. And so that's where we came up with the nucleus today. It was Rutherford that figured out the size of it, and hey, that we have one indeed. So that led to a new model. Now we've got Rutherford's model. We have this small, dense core of positive charges, and the electrons just kind of fly around that empty space surrounding the core. But the math on this just didn't work out. Scientists couldn't figure out, hey, according to math, these electrons would eventually crash into the nucleus. There's nothing holding them out in that open space. So we knew that this model wasn't correct, and it wasn't very long before we got a new model from this guy, Niels Bohr. Niels Bohr looked at absorption and emission spectrums. We'll actually take a much closer look at these tomorrow. And he decided, or figured out, that, hey, the electrons must exist on levels. So we have this picture here. We've got these levels, kind of like orbits, the planets going around the sun, orbiting around the sun. And this is how he figured the electrons must be living in the atom. And they must be held on these energy levels, and similar to how a ladder holds you up. So you can step on any individual rung on the ladder and climb the ladder, but you can't step anywhere between the rungs of the ladder. There's nothing between. So those individual energy levels are like rungs on a ladder. The electrons can be on an energy level, like being on a rung of a ladder, but they can't exist between them. And so this was the Bohr planetary model of the atom. And we're not quite yet to the quantum mechanical model. We'll get to that in a few more days. But this is where I'm going to leave you here for today. Thanks for tuning in.